A kitchen hob is about 7 kilowatts. One AI server rack standing in the floor space of a fridge draws 120. 17 hobs running flat out in a cupboard. And the strange part is that the chips inside it are not the reason. So why did the entire industry suddenly start plumbing water into its buildings? I am Dr. Engineer Lucian Wolf Penlap, and this is AIntelligence. In the next 10 minutes, the chip did not get hotter anything like as fast as the rack did. And I am going to show you in watts exactly where the wall actually is. Because almost everyone, including me 2 days ago, puts it in the wrong place. 4 measurements, 3 corrections to things you have probably been told, and 1 number that I had in my own script wrong until the research came back. If a figure in here is wrong, put it in the comments. I correct on screen, and there is already 1 correction in this episode. AI tells me to keep making them. Start with the thing everybody says. Chips keep getting hotter. It is the most repeated sentence in computing, and at the die it is false. Heat flux is watts divided by area. Prescott, 103 watts across 1.12 square centimeters. And H100, 700 watts, nearly 7 times the power, across 8.14 square centimeters, 7 times the area, 92, then 86. And before anyone says I picked the worst chip of 2004, I did. Prescott was the era's most infamous furnace. A typical 2004 laptop part sat near 24. And against that, the flagship is 3.5 times hotter. So the honest claim is the narrow one. Die heat flux has not risen by anything like the factor rack power has. Hold that thought. Why did power go up and flux stay flat? Because the area went up with it. And that was the only move left once Dennard scaling ended around 2006. Before then, shrinking a transistor cut its power in proportion and density stayed put for free. After, it did not. Moore's law kept delivering transistors. They just stopped being free to switch. So the industry bought parallelism. More cores, more silicon, lower clocks. Which does not mean the die got easier. Same flux, but 7 times the total watts through a heat sink that did not grow. The junction to ambient budget got about 5 times harder. But that is a package problem, and packages got solved. Where the trouble actually went is 1 level up. Not the chip, the box it lives in. A standard rack occupies 600 by 1200 millimeters, 0.72 of a square meter of floor. A conventional enterprise rack in that footprint draws 5 to 10 kilowatts. A current AI rack draws 120. Divide it out, 167 kilowatts per square meter of rack footprint. Spread across the aisles and service space a real hall needs, it is nearer 50. Both numbers get quoted, and only one of them is a floor plan. Here is the first thing worth correcting. That 120 kilowatt figure is the frontier part. It is not what is in the average building. Uptime Institute's 2025 survey puts the typical rack density around 9 kilowatts. The gap between the headline and the estate is more than 10 to 1. Both numbers are true. They describe different buildings. Anyone quoting one without the other is selling you something. But the frontier is where the engineering breaks, so that is where we go. 167 kilowatts per square meter. What does air actually do with that? You will read constantly that air physically cannot cool a 120 kilowatt rack. That turns out to be right for the wrong reason. And the right reason is more interesting. Start with what air can carry. At 20 degrees, it holds about 1200 joules per cubic meter per Kelvin. Allow a 15 Kelvin rise across the rack, the middle of the 10 to 20 band real machines run. 120 kilowatts needs 6.6 cubic meters a second, just under 14,000 cubic feet per minute. Across the equipment face, 9/10 of a square meter, that is 7.3 meters a second, and past 13 through a perforated door. So the stream can carry it. That much is arithmetic. But carrying heat and holding a chip below its limit are two different problems. And I very nearly published only the first one. The number that decides it is the heat transfer coefficient. Air over fins gives you 50 to 250 watts per square meter per Kelvin. A cold plate gives 10,000 to 100,000. Work it through. A 700 watt H100 with 40 Kelvin of headroom needs 0.12 square meters of fin. That fits in 4 rack units, which is why those ship air cooled today. A Blackwell superchip is 5,400 watts in a 1U tray. Same budget, and it needs about 9/10 of a square meter of fin inside a 44 millimeter slot. That is not a fan bill. That is geometry. And there is a second geometry problem underneath it. 14,000 cubic feet per minute is about 22 floor tiles worth of air delivered into a footprint that occupies 1 or 2 tile positions. So the honest sentence has 3 parts. Air can carry the heat. Air cannot hold the junction at that power in that slot height. And if you give it a bigger box, air works again, but then it is not 120 kilowatts in 3/4 of a square meter. The field reached the right conclusion through the wrong mechanism. It is not that the air runs out, it is that the fins do. Getting the heat out is solved expensively. Getting the power in is not. 120 kilowatts into one rack at the 54 volts NVIDIA distributes in rack is 2,222 amps. That is a bus bar, not a cable. Copper has resistance. Push that current far enough and you lose real percentage points before the silicon sees a watt of it, which is why 800 volts direct current is coming full production in 2027. Not for efficiency, though it gains a few points. For copper, 200 kilograms of bus bar to feed a 1 megawatt rack at 54 volts and nowhere to put it. And one step further out, the constraint stops being electrical engineering at all. A campus drawing hundreds of megawatts needs a grid connection, and a grid connection is not a purchase, it is a queue. In Europe's 5 biggest data center hubs, the IEA puts the average wait at 7 to 10 years. That was November last year. So the stack of limits, in the order they actually bite. The die is not the one that broke first. It has its own troubles, and they are the next episode. The rack got dense. The room became a geometry problem, and the grid is the wall. The chip did not get hotter. Everything around it got denser, and the last thing in the chain is the slowest to build. Everything from here is speculation, and it is marked as such. If the grid is the binding constraint, the interesting engineering stops being cooling and becomes where? Put the compute where the power already is. Kenya has exactly that. Firm geothermal at Olkaria already generating. And it does not solve it. A campus the size of the ones going up in Virginia would be about a third of Kenya's entire grid-connected capacity. Power that already exists is still not a socket. Every figure in this video with its source and the date I checked it is in the description. 17 hobs in a cupboard. The chips were never the reason, and I got there by being wrong twice. I thought die heat flux was the wall. It is not. Then I said air could do it, and only the fan bill stopped it. That was wrong in the other direction. Both are on screen because they should be. If you find the next one, the comments are open.